All right, chemistry, this is your video lecture for Chapter 2, Section 2, Part 2. We're continuing to talk about units of measurements. In this video lecture, I want you to be able to distinguish between mass and weight. I want you to be able to perform volume calculations, perform density calculations, and then transform a statement of equality into a conversion factor. So here we go. So the mass of an object is the quantity of material it contains. Mass is measured on a balance. You're comparing whatever object you have to an established standard. You're balancing the two. Mass uses the unit grams in the metric system and uses the unit kilogram in the SI system. But when we compare mass to weight, even though we use those two words very interchangeably in the English language, they are not the same. For example, mass is the quantity of matter, how much space it takes up, measured with a balance, uses grams or kilograms for the unit, whereas weight is a force, the force of gravity pulling on that matter. So you have matter, you have mass. When gravity acts upon that mass, the measured force of that is weight. It's measured with a spring scale, not a balance. You're just allowing gravity to accelerate that object downwards, and then you're measuring that force. The unit is newtons. The unit is newtons. Moving on to volume. Volume is the space occupied by a substance. Volume uses the unit liter in the metric system or cubic meters in the SI system. As a statement of equality that may be useful coming up, 1 liter is equal to 1.057 quarts. Volume is also measured using a graduated cylinder, and some volume calculations that we'll be carrying out later will use graduated cylinders. Looking at area. Area is a derived unit because, if you remember from math class, area equals length times width. For example, this rectangle is 3 meters by 8 meters. Okay, and so if we're going to calculate the area of this rectangle, we're going to multiply 3 by 8. Everyone at this level of science class already knows that. You multiply 3 times 8 to get 24. And you probably remember that the unit for area is meters squared, but do you remember why, or can you figure out why? Most people know that we multiply 8 times 3 because we're multiplying length and width. But do you also know that you multiply the units as well? So we multiply 8 meters by 3 meters, and we get 24 meters squared. Now, why does it become squared? Well, we know that 8 times 3 is 24. That's pretty easy. But what is meters times meters? Well, it's meters times itself, aka meters squared. Volume's closely related, but we have yet another dimension. We don't just have length and width, and we now have height. Sometimes you'll use the term depth, but we're just referring to this third dimension. Very similar to the way we calculate area, we calculate volume by multiplying the length times the width times the height. In this example of a cube, I have 4 meters on each side, so I will carry out 4 meters times 4 meters times 4 meters. Now 4 times 4 times 4 is 64, but meters times meters times meters is meters cubed, or cubic meters. And so the volume of this cube is 64 meters cubed. Now, what we want to do here as a sample problem is we want to find the volume of this cuboid, this weird-looking cube. Now, over here on the left, this is 6 by 3 by 2. So we're going to use the equation that we saw on the last slide. It's going to be 6 meters times 3 meters times 2 meters. Now, 6 times 3 times 2 is 36, and meters times meters times meters is meters cubed. We're going to do the exact same thing over here on the right. 10 centimeters multiplied by 4 centimeters multiplied by 2 centimeters. Again, length times width times height still applies here. So I go 10 centimeters multiplied by 4 centimeters multiplied by 2 centimeters. Now that's going to equal 80 centimeters cubed, or cubic centimeters. These are both units of volume, even though obviously a cubic meter is larger than a cubic centimeter. Now, if we're trying to figure out the volume of some irregular shape that's not a cube or cuboid, something that's very convenient to calculate, we use graduated cylinders or some sort of container that can hold water. So if we have this weird looking shape, this irregular shape, we're going to, in our example, we're going to partially fill a graduated cylinder with water. And we're going to measure the level of that water. In this example, we start at 50 cubic centimeters. We then lower the object into the water. Be careful not to splash. You don't want to lose any of the water. We don't even want to have the water splash up onto the sides of the graduated cylinder. But we insert the object into the water and we measure the new level. The difference between those two levels is going to be the volume of the object. So in this case, the water level started at 50 cubic centimeters, and then once we placed the object into the graduated cylinder, the volume became 70 cubic centimeters. That's an increase of 20 cubic centimeters. Where did that 20 cubic centimeters come from? The object. So I'd like you to try this on your own. Find the volume of this irregular shape. So initially we had a water level of 50 cubic centimeters. After the irregular object was placed into the graduated cylinder, we have a volume of 83 cubic centimeters. So simply calculating the difference will give us the volume of the irregular shape, and that will be 33 cubic centimeters. Now, there are a number of different units for different quantities. For example, for volume, you might see cubic meters. You might see cubic centimeters. You might see cubic decimeters. You might see liters, and you might see milliliters. In order to convert back and forth between any of these, simply use the statements of equality. 1 cubic decimeter is equal to 1 liter, and 1 cubic centimeter is equal to 1 milliliter. Using these statements of equality, you'll be able to convert back and forth between any of these units. Density. Density is the amount of mass per unit volume of a substance. SI uses kilograms per cubic meters. More common units that we will actually use more commonly in this course, we have grams per cubic centimeter and grams per milliliter. Now going back one slide, I want to point out that 1 cubic centimeter is the exact same thing as 1 milliliter. The exact same volume. So when we say that a common unit for density is grams per cubic centimeter or grams per milliliter, those are actually the exact same thing. They're the exact same thing. We simply may choose cubic centimeters over milliliters or vice versa because it's more convenient for what we want to convert into. And so when we're comparing the densities of two things, we're always keeping the volume constant. So if we need to divide that out, we'll do that. For example, notice we have steel, wood, and air down here. It's a 1 cubic meter cube of these three different substances. But notice, even though the mass is changing, how many kilograms there are, the volume is staying the same. It's 1 cubic centimeter, or 1 cubic meter, 1 cubic meter. And then air also is per 1 cubic meter. So this means in 1 cubic meter of steel, there's 7,800 kilograms. In 1 cubic meter of wood, it's 500 kilograms. And in 1 cubic meter of air, there's 1.2 kilograms. So, how are we going to do calculations involving density? Suppose lead has a mass of 22.8 grams, and it has a volume of 2.00 cubic centimeters. What's the density? So we've been given two pieces of information. We've been given mass, and we've been given volume. Now, density is equal to mass divided by volume, right? Grams per cubic centimeter. And so since we have grams and cubic centimeters, because we've been given the mass and the volume, we can simply plug those straight in for a calculation. 22.8 grams divided by 2.00 cubic centimeters. The calculator lets me know that that is 11.4 grams per cubic centimeter. Now, the international system, the SI system, the internationally agreed upon choice of metric units. It consists of base units from which all other units can be derived. I referred to this earlier. The quantities of mass, length, volume, temperature, and time are what are known as base units, and using these by either multiplying by themselves or something else, or dividing by themselves or something else, you can derive any unit you need. Anything that you derive from these base units would be known as a derived unit. So the metric system is based on a decimal system, based on 10, base 10. And one of the reasons that this is very, very easy is because we are able to convert between orders of magnitude in the metric system very, very easily. And we use prefixes. We use prefixes. Now, you've probably heard of most of these, but in this course, you'll have to become familiar with what they actually denote. So prefixes like mega, kilo, hecto, deca, deci, centi, milli, micro, nano, pico, or femto. These all have a certain exponent associated with them, and you will have to use these to convert back and forth between different units. So let's see how we're doing so far. For each of the following, meaning the A, B, and C, indicate whether the unit is a length, a mass, or a volume. Go and press pause now. So A bag of tomatoes is 4.6 kilograms. Well, kilograms is a unit of mass. A person is 2 meters tall. Meters is a unit of length. Medication contains 0.50 grams of aspirin. Grams is a unit of mass. The bottle contains 1.5 liters of water. Liters is a unit of volume. Try one more. Now identify the measurement that has an SI unit. SI unit specifically, not empirical and not metric, but SI unit. Go ahead and press pause now. So the thing I'd like to point out is that a lot of these measurements are actually the same. Not all of them, but a lot of them are actually the exact same amount. They're just using different units. So for A, Johnny's height is, which one is an SI unit? Meters. Okay, so 2.1 meters. The SI unit for time is seconds. The mass of a lemon in SI units is kilograms. And then temperature in the SI system is Kelvin, on the Kelvin scale. We're going to finish up with conversion factors. Now, I will warn you that these aren't the simplest thing, but they're certainly not the most complicated thing, and they will last the entire course. A huge amount of what you're required to do in the rest of this course, especially second semester, is based on your ability to use conversion factors. So please stress this in your studying. Now, a conversion factor is a ratio derived from the equality between two different units that can be used to convert from one unit to another, and we will be doing this a lot. For example, I know that if I have 4 quarters, I have $1. They're the exact same amount of money. So if I were to divide an amount of money by itself, by that same amount of money, I get an answer of 1, right? So 4 quarters divided by $1 is 1, because they're the exact same amount of money. Similarly, I can divide $1 by 4 quarters. The exact same amount of money. It's amount of money divided by itself. It's just 1. Or 0.25 quarters, or sorry, $0.25 divided by 1 quarter, that equals 1, because it's the exact same amount of money. And when we create a conversion factor, we are going to base our construction of these conversion factors on this fact. So a conversion factor, when you divide it out, it has to equal 1, meaning the numerator has to be the exact same thing as the denominator. They have to be equal. So, for example, if I'm going to convert 5 kilometers into meters, I would take my 5 kilometers and I would create a conversion factor. I know that for every 1 kilometer, I have 1,000 meters. And so what I do is I have a fraction. So on the numerator, the top, I place the new unit, the unit into which I am wanting to convert. On the denominator, the bottom, I place the old unit, what I want to convert away from. Now, the reason I want to have the old unit on the denominator is so that those units can cancel out. Because when you divide something by itself, it equals 1. And if you're multiplying anything by 1, it doesn't change the value of that measurement, and so there's no need to include the 1. You can not include it. So you basically have the ability to have the kilometers here completely disappear. They cancel out. So I'm left with meters. Meters, that M is the only unit I have left because the kilometers canceled themselves out. And so the unit of my answer is going to be the only unit that's left, meters. And so I simply carry out the mathematical function that's left to me is 5 times 1,000 for an answer of 5,000. All right, let's try one more. We're going to convert 7,000 meters into kilometers. So we have the 7,000, and we're going to multiply that by a conversion factor. Now, meters here is what I'm starting with, so I want to convert away from meters and into kilometers. So that'll let me know that I want to put the meters on the denominator and the kilometers on the numerator, so that meters will cancel. They're gone. I don't have to write that M anymore. The only unit I have left is the kilometers. So my answer will be in terms of kilometers. Now this calculation is telling me, the way it's set up, that I'm going to divide 7,000 by 1,000. That comes out to be 7. All right, chemistry, so what we've done so far in this entire section, not just this video, we've distinguished between a quantity, a unit, and a measurement standard. We've named SI units for length, mass, time, volume, and density. We've distinguished between mass and weight. We've performed volume calculations as well as density calculations. And then we've transformed a statement of equality into a conversion factor. All right, chemistry, I will see you next period.